Yeah, hello everyone, welcome back. I'm your friend in XO. Today we're going to learn the exponential models. I'm pretty sure I didn't learn that before. What is called exponential models? Interpreting change in exponential models.
So I've taken some screenshots of the Khan Academy interpreting rate of change for exponential models in terms of change. Maybe they're going to change the title. It seems a little bit too long. But anyway, let's actually just tackle these together. So the first day of spring, an entire field of flowering trees blossoms. The population of locusts consuming these flowers rapidly increases as the trees blossom. The relationship between the elapsed time t in days since the beginning of spring and the total number of locusts, L of t, so the number of locusts is going to be a function of the number of days that have elapsed since the beginning of spring, is modeled by the following function. So locust as a function of time is going to be 750 times 1.85 to the tth power. Complete the following sentence about the daily rate of change of the locust population. Every day the locust population, well, every day, think about what's going to happen. I'll draw a little table just to make it hopefully a little bit clearer. So let me draw a little bit of a table. So we'll put t and L of t. So when t is 0, so when 0 days have elapsed, well, there's going to be 1.85 to the 0th power. This is going to be 1. So you're going to have 750 locusts right from the get-go. Then when t equals 1, what's going to happen? Well, then this is going to be 750 times 1.85 to the first power. So it's going to be times 1.85. When t is equal to 2, what's L of t? It's going to be 750 times 1.85 squared. Well, that's the same thing as 1.85 times 1.85. So notice, and this just comes out of this being an exponential function, every day you have 1.85 times as many as you had the day before. 1.85. So we essentially take what we had the day before and we multiply by 1.85. And since 1.85 is larger than 1, that's going to grow the number of locusts we have. So this is going to grow. I'm not on the website right now, so that's why normally there would be a drop down here. So I'm going to grow by a factor of 1.85 every day. Let's do another one of these. All right, so this one tells us that Vera is an ecologist who studies the rate of change in the bear population of Siberia over time. The relationship between the elapsed time t in years since Vera began studying the population and the total number of bears, n of t, is modeled by the following function. All right, fair enough. It's got a little exponential thing going on. Complete the following sentence about the yearly rate of change of the bear population. Let's just think about every year that passes. T is in years now. Every year that passes is going to be 2/3 times the year before. I can do that same table that I just did just to make that clear. So let me do that. Whoops. Let me make this clear. So table. So this is t, and this is n of t. When t is 0, n of t, you're going to have 2,187 bears. So that's the first year that she began studying that population. 0 years since Vera began studying the population. The first year is going to be 2,187 times 2/3 to the first power, so times 2/3. The second year is going to be 2,187 times 2/3 to the second power, so that's just 2/3 times 2/3. So each successive year, you're going to have 2/3 of the bear population of the year before. You're multiplying the year before by 2/3. So every year the bear population shrinks by a factor of 2/3. All right, let's do one more of these. So they tell us,
Well, it's kind of boring. This is too simple. If you get a base number, if it's greater than 1, then the result will be always grow. But if it's less than 1, the result would be always decrease or shrink.
after a special medicine is introduced into a petri dish full of bacteria, the number of bacteria remaining in the dish decreases rapidly. The relationship between the elapsed time t in seconds and the number of bacteria n of t in the petri dish is modeled by the following function. All right. Complete the following sentence about the half-life of the bacteria culture. The number of bacteria is halved every blank seconds. So t is being given to us in seconds. So let's think about this a little bit. Let's think about it. I'll draw a little table here. So if we have, this is t, and this is n of t, and I'll start with a straightforward t. At time equals 0, right when we start, this whole thing, if this t is 0, then 1/2 to the 0 over 5.5 power, that's just 1/2 to the 0. That's all going to be 1, and you're just going to be left with 1,000 bacteria in the petri dish. Now, at what point do we get to multiply by 1/2? At what point do we get to say 1,000 times 1/2? Well, in order to say 1,000 times 1/2, the exponent here has to be 1. So at what time is the exponent here going to be 1? Well, the exponent here is going to be 1. This whole exponent is going to be 1 when t is equal to 5.5 seconds. So t is 5.5 seconds. And likewise, if we wait another 5.5 seconds, so if we go to 11 seconds, then this is going to be 1,000 times 11 divided by 5.5 is 2. So times 1/2 to the second power. So times 1/2 times 1/2. So every 5.5 seconds, we will essentially have half of the bacteria that we had 5.5 seconds ago. So the number of bacteria is halved every 5.5 seconds. And you see it in the formula, or in the function definition right over there. But it's nice to reason it through and to really digest why it makes sense. Let's do a few more of these. The chemical element Einsteinium-253 naturally loses its mass over time. A sample of Einsteinium-253 had an initial mass of 320 grams when we measured it. The relationship between the elapsed time t in days and the mass m of t in grams left in the sample is modeled by the following function. Complete the following sentence about the rate of change in the mass sample. The sample loses 87.5% of its mass every blank days. So this one, instead of saying how much we grew or shrunk by, we're saying a percent change. So if you lose 87.5%, that means that you are left with 12.5%. 12.5%, which is the same thing as that you have, is the same way of saying that you have 0.125% of your mass. So another way of thinking about it is the sample is 0.125 of its mass, of its original mass, or how long does it take for the sample to be 0.125 of its mass? And there we could do a similar idea. You see the 0.125 right over here. And so I could draw a table if you like, although I think you might guess where this is going. But let me draw a little table here. So t and m of t. When t is 0, m of t is 320. And so at what point is t, at what time is m of t going to be 320 times 0.125? Because this, going from this to this, that is losing 87.5% of your mass. Losing 87, so let me just write it this way. So this is minus 87.5% of the mass. You've lost 0.875 to get to 0.125. So this, you could just use 0.125 to the first power. So what t do you have to make this exponent equal 1? Well, t has to be 61.4. 61.4, and where t is in days. 61.4 days. Now you might be tempted to always just pattern match. So whatever's in the whatever's in the denominator here. But I really encourage you to think about it, because that's the whole point of these problems. If you just are pattern matching these, well, I don't know how helpful that's going to be for you.
To be honest, I do not know anything about that question, but here's the thing. If you set the t equal to 0, this part will always be 1, and 320 times 1 would always be 320. And again, if you want to lose this kind of percentage, then you probably times your orange number by 1 minus 0.84, which is exactly this one, 0.125. And how can you get such a result? Well, when your exponents equal to 1, then that's possible. But how can we let this part equal to 1? How can we do that? Well, we just have to let the numerator and the denominator be the same, which is equal to this value. Then we're done. Constructing exponential models according to rate of change.
Derek sent a chain letter to his friends, asking them to forward the letter to more friends. The group of people who receive the email gains 9/10 of its size every 3 weeks and can be modeled by a function p, which depends on the amount of time t in weeks. Derek initially sent the chain letter to 40 friends. Write a function that models the group of people who received the email t weeks since Derek initially sent the chain letter. So pause the video if you want to have a go at this.
Alright, we really want to do it by ourselves. So let's say Derek sent a chain letter to his friends, asking them to forward the letter to more friends. The group of people who receive the email gains 9/10 or 9/10 of its size every 3 weeks and can be modeled by a function p, which depends on the amount of time t in weeks. Derek initially sent the chain letter to 40 friends. So write a function that models a group of people who receive the email t weeks, then Stark initially send the chain letter. Very well. Even for this little simple problem, I guess it's a simple problem, I have no idea how to make it right. So at the beginning, we got 40 letters. Then what's next? He sent these 40 letters to his friends, ask them to forward the letter to more friends. The group of people who receive the email gains 9/10 or 9/10 of its size every 3 weeks and can be modeled by a function p, which depends on the amount of time t weekends. So now our mission is to get the p function. I guess it should be something like this. 40 times the base number, which is 9/10, and to the power of t divided by 3. I guess that's it. I don't know if it's correct. Alright, then let's get into the video.
Alright, now the way I like to think about these, let's just create a table with values for t and our function p, which is a function of t, for some values that we can just pull out of the description here. So when t is 0, when it's been 0 weeks since Derek initially sent the chain letter, how many people have gotten it? Well, they tell us. Derek initially sent the chain letter to 40 friends. So t equals 0, p of t, or p of 0, is 40. Now, what's an interesting time period here? It says that the number of people who've received the email gains 9/10 or increases by 9/10 every 3 weeks. Every 3 weeks. So after 3 weeks, so 3 weeks have gone by, so I'm just adding 3 to t. What is p of t going to be? Well, they tell us it's going to gain 9/10 of its size. So it's going to be 40 plus 9/10 times 40, which is going to be equal to what? Well, that's equal to 40. If we factor out of 40, 40 times 1 plus 9/10. Or you could say this is equal to 40 times 1.9. Or another way of thinking about it, after 3 weeks, we've grown 90%. That's another way of saying that the number of people who receive the email gains 9/10 of its size. You could say the group of people who receive the email grows 90% every 3 weeks. And so if we go another 3 weeks, so plus another 3 weeks, I could say, well, let me just write, this is 6 weeks. Well, how many people will have received the email? Well, it's going to be this number, and it's going to be grown another 90%. So we're going to multiply it times 1.9 again. So it's going to be 40 times 1.9 times 1.9. We're going to grow by another 9/10. Growing by 9/10 is the same thing as multiplying by 1 and 9/10. The 1 is what you already are, and then you're growing by another 9/10. So this is the same thing as 40 times 1.9 squared. You go another 3 weeks, 9 weeks, we're going to grow another 90%. So you're going to take this number and multiply by 1.9 again, which is going to be 1.9 to the third power. And so what's going on over here? Well, we can see it's an exponential function. We have our initial value, and every 3 weeks we're multiplying by 1.9. So 1.9 would be our common ratio. So we could say that P of t is equal to our initial value, 40, times our common ratio, 1.9, and we multiply by 1.9 every 3 weeks. So we could just say how many 3-week periods have passed by? Well, we will take t and divide it by 3. T divided by 3 is the number of 3-week periods that have gone by. And there you have it. And notice, t equals 0. 1.9 to the 0th power is 1. So 40 times 1. T equals 3. That's going to be 1.9 to the first power, 3 over 3. And so we're going to grow by 90%, and so on and so forth. So feeling pretty good about this. That's going to be 1.9 to the...
So it seems like we probably got it right, but we missed one part of it. Here, instead of line tenths, we should say 1 plus like 9 tenths. That's the final answer for us. So we kind of made it correct. Let's go.
Ocean sunfishes are well known for rapidly gaining a lot of weight on a diet based on jellyfish. The relationship between the elapsed time t in days since an ocean sunfish is born and its mass m of t in milligrams is modeled by the following function. All right. Complete the following sentence about the daily percent change in the mass of the sunfish. Every day there is a blank percent addition or removal from the mass of the sunfish. So one thing that we know from almost from the get-go, we know that the sunfish gains weight, and we also see that as t grows, the exponent here is going to grow, and if you grow an exponent on something that is larger than 1, m of t is going to grow. So I already know it's going to be about addition to the mass of the sunfish. But let's think about how much is added every day. Well, let's think about it. Well, let's see if we can rewrite this. I'm going to just focus on the right-hand side of this expression. So 1.35 to the t over 6 plus 5. That's the same thing as 1.35 to the 5th power times 1.35 to the t over 6th power. And that's going to be equal to 1.35 to the 5th power times 1.35, and I can separate this t over 6 as 1/6 times t. So 1.35 to the 1/6 power, and then that being raised to the teeth power. So let's think about it. Every day as t increases by 1, now we can say that we're going to take the previous day's mass and multiply it by this common ratio. The common ratio here isn't, the way I've written it, isn't 1.35. It's 1.35 to the 1/6 power. Let me draw a little table here to make that really, really clear. And all of that algebraic manipulation I just did is just so I could simplify this so I have some common ratio to the teeth power. So t and m of t. So based on how I've just written it, when t is 0, well, as t is 0, this is 1. So then we just have our initial mass is going to be 1.35 to the 5th power. And then when t is equal to 1, it's going to be our initial mass, 1.35 to the 5th power, times our common ratio, times 1.35 to the 1/6 power. When t equals 2, we're just going to multiply what we had at t equals 1, and we're just going to multiply that times 1.35 to the 1/6 again. And so every day, every day we're growing by our common ratio, 1.35 to the 1/6 power. Actually, let me get a calculator out. We're allowed to use calculators in this exercise. So 1.35 to the open parentheses, 1 divided by 6, close parentheses, power is equal to 1.05, I'll say 1.051 approximately. So this is approximately 1.051. So we could say this is approximately 1.35
Here's another way to express the approximately value or let me say this. Approximate value. Well, you do this. You say B is approximately A, where the B is the original number, the A is the simplest number. So if I have a number called 2.1 and another number I call it 2, I would say 2.1 is approximately 2.
1. So we could say this is approximately 1.35 times 1.051 to the tth power. So every day we are growing by a factor of 1.051.
And if you want to express this expression in a natural language way, what you could say is that for every day or for every t plus 1, we are growing by a factor of this number right here.
Well, growing by a factor of 1.051 means that you're adding a little bit more than 5%. You're adding 0.51 every day of your mass. So you're adding 5.1%. And if you're rounding to the nearest percent, we would say there's a 5% addition to the mass of the sunfish every day.
The last one, let's get into it.
The amount of carbon dioxide, CO2, in the atmosphere increases rapidly as we continue to rely on fossil fuels. The relationship between the elapsed time t in decades, let me highlight that because that's not a typical unit, but in decades since CO2 levels were first measured, and the total amount of CO2 in the atmosphere, so the amount of CO2 A of subdecade of t, in parts per million is modeled by the following function. So the amount of CO2 as a function of how many decades have passed is going to be this. So t is in decades in this model right over here. Complete the following sentence about the yearly rate of change. The yearly rate of change in the amount of CO2 in the atmosphere. Round your answer 2 decimal places. Every year, the amount of CO2 in the atmosphere increases by a factor of, if they said every decade, well, this would be pretty straightforward. Every decade, you increase t by 1, and so you're going to multiply by 1.06 again. So every decade, you increase by a factor of 1.06. But what about every year? And I always find it helpful to make a bit of a table just so that we can really digest things properly. So I'll say t, and I'll say a of t. So when t is equal to 0, so at the beginning of our study, well, 1.06 to the 0th power is just going to be 1. You have 315 parts per million. So what's a year later? So a year later is going to be a tenth of a decade. Remember, t is in decades. So a year later is 0.1 of a decade. So 0.1 of a decade later, what is going to be the amount of carbon we have? Well, it's going to be 315 times 1.06 to the 0.1 power. And what is that going to be? Well, let's see. So 1.06 to the 0.1 power, I didn't have to actually use a parentheses there, is equal to 1.0058. I'll just stick it with that. It's 1.0058. So this is the same thing as 3.5 times 1.0058. And I should say approximately equal to. I did a little bit of rounding there. So after another year, so now we're at t equals 0.2. We're at 2/10 of a decade. Where we're going to be? We're going to be at 3.5 times 1.06 to the 0.2, which is the same thing as 3.5 times 1.06 to the 0.1, and then that raised to the second power. So we're going to multiply by this 1.06 to the 1/10 power again, or we're going to multiply by 1.0058 a second time. Another way to think about it, if we want to reformulate this model in terms of years, so per year of t, it's going to be 315, and now our common ratio wouldn't be 1.06, it'd be 1.06 to the 0.1 power, or 1.0058 and then we would raise that. Now t would be in years now. Here it is in decades. And I could say approximately, since this is rounded a little bit. And so every year the amount of CO2 in the atmosphere increases by a factor of, I could say 1.06 to the 0.1 power, but if I'm rounding my answer to 2 decimal places, we're going to increase by 1.0058. In fact,
all right. So let's say at the beginning, the question. What does the question give to us? It says that let's say it gives us an expression based on decades. Then what we did here is to convert that decades to a year unit of t. And how we make it done? We simply we did a scale kind of thing. We calculate out the 0.1 version and 0.2 version of t. And after that, we found the foundation, which is this one. Because for each time, we just have to multiply itself by 1, and then we get the base. The base is actually this number, 1.0058. Alright, so let me say for the whole section of this unit, what it does is to teach us how can we use our knowledge, especially the exponential stuff, how can we apply those ideas, those concepts into real life problem. It has a common usage. For example, in real life, if you save your money into a bank, you probably would get some revenue or profits from that bank for each year. For example, 0.1% of profit each year for your money. And for this case, if you want to calculate the money you can get from that bank over years, for example 3 years, then you probably wanna use something like this. You're gonna multiply it by you're gonna raise that number to the power of 3. Okay, that's one using example for that exponent idea. Okay, so I think this is today's learning, and I'll see you guys in the next one. Bye.